There's another thing about this curve is in that also that in recent times, I mean really recent times, then there is a group from Berkeley headed up by a physicist, a U.S. lab physicist from Lawrence Livermore, and they've actually set out themselves to try to disprove this curve, that the methodology that's used in this curve then can be shown to be false, and that we're not really dealing with a situation where global temperatures are warming. So far, their efforts have sort of not shown this to be the case. In fact, what they've managed to do is to sort of replicate this curve, which is probably a bit of a disappointment. So that's just one thing, right? This is then, I would say, it's as factual as we can sort of get with scientific information from parts of climate. John may want to comment on that afterwards. Now, this is the other curve that sort of always gets my attention in here, and this is known as the Keeling curve. And the Keeling curve then was produced by at one time then, one of the students that was in the class being taught by Professor Keeling in here was Al Gore, okay? And so it's probably then the class that Al Gore took from Professor Keeling when Al Gore was an undergraduate student then in here, that sort of influenced him in a lot of his ideas about changes in the atmosphere of the Earth. And clearly what this curve shows then is that as time is progressing in here, shown on here from 1960 to the present day then, that the amount of carbon dioxide in the atmosphere then is increasing. And if we look at the sort of expand the last part of that curve in here, then what we would see is that the amounts of carbon dioxide in the atmosphere are in the order of 390 parts per million. Okay, it's quite a large number, as we'll see on Earth. Now, the importance of the carbon dioxide molecule in here and the greenhouse effect is something well known to chemists, and we have a chemist with us tonight. And if we have questions then about the vibration of the carbon dioxide molecule and the way that it can absorb energy and then re-emit and warm the atmosphere, we've got Kent Rogers. He's trying to hide at the back of the room there, but we'll be able to ask him specifically for some explanations on that, the actions of the carbon dioxide molecule and why then it's important in this story. So now I'm going to go on from this curve, though, keeping in mind that number, 390 parts per million in there. And I'm going to talk about something which is a little bit closer to my own efforts in sort of research, although still a long way in reality. But it involves geology and geochemistry, and it involves ice cores, and it particularly involves then work that's been done on the great ice sheets of the Earth today, Antarctica for one, but also Greenland in the northern hemisphere for another. Ice can be cored, as you can see then in this particular image in here. On the right, you can actually see, looking down a microscope, you're looking at some crystals of ice under a microscope, and you can see some black, sort of circular, ovoidal type shapes that are in the ice as you're looking at the section of the crystalline ice in there. And those bubbles that are in there, this would be referred to as bubble ice, okay, by the scientists that work on these ice cores. That bubble ice then actually contains fossilized atmosphere from times past in here. And using obviously pretty sophisticated techniques in here then, that fossil air can be released and it can be used to measure then concentrations of atmospheric gases directly. And this has been done now on several ice cores, and the patterns then that are received from those ice cores are pretty similar. So I'm going to show you some results then of the ice core studies. Once again, shown as a graph, so I apologize for these graphs. Oops. Now, I hit the wrong button. How do I just do that? Yeah, okay. So, this is the curve then that I'll show you, and I'll make a couple of points off this particular curve. First of all, you can see then on the left-hand end of the curve is zero on there, and on the other end is 650,000. This is on the horizontal axis, okay? So this is an ice core then. It's one of the later ice cores that's been drilled, and it represents about 650,000 years of record. And on the top part of the curve, okay, it shows then measurements from bubble ice, okay, the measurements directly of carbon dioxide in the atmosphere that have been taken from this particular Antarctic ice core. And what it shows then is a series of peaks in carbon dioxide values, and they reach a number around about 300 parts per million, okay? The latest peak at 0 in there is a number near where we are today. As we'll see, we're actually above that number at the present day, okay? We go back to the next peak, that's back there at about 120,000 years ago. That's the peak of the last interglacial on Earth. In between then is the last glaciation. So one thing that we learn in here then, that during interglacials, warm times, values of carbon dioxide are high. During glacials, when the Earth is cold, values of carbon dioxide are lower. And on the bottom then, there is a curve. It's sort of broken up into two pieces and made probably unnecessarily complicated on here. But just sort of follow one of the tracks on there. This is a proxy from the ice core records of temperature. This is derived independently then of that carbon dioxide measurement. So it would be there regardless of what's happening with the carbon dioxide measurement. And what it shows then is that there is a tracking on this curve. So this is one important thing that comes out of ice core information, is that temperature then tracks carbon dioxide values in these ice cores. Now we can get into arguments about chickens and eggs in this, but let's just say at the moment there's a tremendous parallelism in here. And most scientists of my type, at any rate in here, would argue in here that this is a linkage that is a very important linkage as we try to come to grips with the ideas of greenhouse gases and climate change. Now, the other thing that is important, I think, on this curve in here to me is that when we look at the values, measured values of carbon dioxide from these curves then in here, we see that we get an upper value of about 300 parts per million, and it never goes really above that value. And we get a lower part then in there that goes down to values of about 180 parts per million. It stays about that same. So it looks then that there's something happening on Earth, in the natural Earth in here, over the hundreds of thousands of years, where there is processes that are happening that are occurring on Earth then that keep the carbon dioxide, the natural carbon dioxide on Earth then within certain boundaries on here. Now, we can go to the present day, and we see then that values of carbon dioxide at the present day then are well above those that can be measured in ice cores in here. They're 390 parts per million and growing. Okay, those numbers are growing in here. So the question then would be, and here I guess, to most of us who look at these problems, where on Earth is this additional carbon dioxide coming from if it's not coming from anthropogenic type of causes? We hear explanations about warming oceans and oceans giving up carbon dioxide, but they don't seem to work in terms of any explanations we can come up with. So for most scientists of my type, the notion that we are contributing to this carbon dioxide then is very real in that respect. So here's just a summary then of general reasons why we are concerned about these carbon dioxide in the atmosphere. We've got these very high values of carbon dioxide. We can see 390 parts per million. We've got carbon dioxide that's obviously increasing every year in here, and it's now 10% higher than it was 20 years ago. If we look at those ice core records, then we see values of in the ice then that of the present day, I should say, that are higher than they have been on Earth for the last 650,000 years. We've had this high concentration of hotter years since 1990 than we have earlier. Each of these agencies, NOAA, of course, American, Hadley, coming from the UK, NASA, once again, one of our own agencies in here. Each one of them will pick different years as the hottest years in here, but together they still show the same patterning of these hottest years. We also see with that then some other tendencies on Earth, right, that sea ice in the Arctic is at lower levels than we've seen. The trends in sea ice, at any rate, at the lowest levels that we've seen for most of the last 100 years, at any rate. We see then in Antarctica that ice shelves are breaking up in Antarctica. We see mountain glaciers retreating, and we see that sea level, even though it is not showing really truly significant rises at this time, is actually, on the trend, is moving up at about 3 millimeters a year. So we see these tendencies which have us sort of generally concerned into the future. So what I'd like to talk about now is a little bit about shifting then from the global picture of changes in here to looking at the region. So, you know, can we sort of try to explore a little bit what some of these changes might mean to our region in here, in parts of the story at any rate. Obviously there could be things in agriculture that we're not going to get into and other things like this, but let's have a look at some of these regional changes. First of all, this notion of temperature in here. So this is just taking data that's available then from various climate agencies that are available on the web, and it's taking then the four corners, if you want, of North Dakota in here. And so we can look at the period then from the year 1900 up until more or less the present, okay? And what we can see then in the four corners of North Dakota, then we are surrounded, right, by these communities in North Dakota. We can see that what we expect for temperature records for the Great Plains. We see there's a lot of variation in the temperature records. They go up and down and up and down and up and down. But when you look at them statistically in here then, what you see is that there is a trend upwards in each one of them. And if you look at that trend, the amount of difference in temperature change, what that actually makes, then through these different curves in here, then it is not so different than that global picture of temperature change that's seen. So North Dakota is part of this story, is part of that global curve. We're not anything different. There's nothing here that is making us go backwards or something like that. We are in step then with the types of increases we're seeing in global temperature curve in North Dakota. Now, along with that, we also see that growing season is changing in North Dakota. And so we can say then that by the year 2030, using this information then that comes from Adnan Akuz, who's a climatologist up at NDSU, we can say then in the year 2030 then that the average length of growing season will be 2 to 3 degrees longer than it is today in here. If the trend continues, clearly, but it's been a pretty persistent trend that we're looking at over this 100 years or so. Now, what this could mean then in terms of the city, right, and if you're a gardener in here, it could mean that you can suddenly start to have some plants which we may be able to grow in our gardens. We might be able to plant certain trees on our boulevards that we weren't able to plant before, because now we've gone across the threshold for their tolerance in this slightly different world of the year 2030 in here. So hopefully as city forester and others will be looking at these curves and thinking about what it might mean then in terms of other possibilities for greening up our city into the future.